Today we'd like to look at the concept of symmetry. Symmetry occurs frequently in nature. A butterfly has wings that are symmetric to each other. Generally speaking, animals are approximately symmetric. They have one eye on each side of their face. Our hands are reflections of each other. If we see a bridge, usually one side of the bridge is the same as the opposite side if you look and compare it with the center line. We see symmetry quite a bit in architecture as well. Today we want to look at symmetry in mathematics and in our functions and equations. The first thing we want to look at is the graph of x equals y squared. And if we compare the point 4, 2 and 4, negative 2, we see these are reflections of each other across the x-axis. And so for any point xy, the point x and negative y would be a reflection across the x-axis. And so we would say 4, 2 and 4, negative 2, or the point x, comma y and x, comma negative y. These points are said to be symmetric with respect to the x-axis and are reflections of each other across the x-axis. And we'll find the same thing is true if we look at the graph of y equal to x squared minus 5. We find that that will go through the point 3, 4 and negative 3, 4. And if we draw this graph, we can see that these 2 points, negative 3, 4 and 3, 4, are equidistant from the y-axis. And any general point then x, y, and negative x, y, these 2 points would be reflections of each other across the y-axis also. And we would say 3, 4 and negative 3, 4, or x, y and negative x, y are symmetric with respect to the y-axis. And so these are reflections across the y-axis. And so we would say the whole graph then of this parabola here is symmetric with respect to the y-axis, and the previous one we looked at, the graph of this parabola is symmetric with respect to the x-axis. Now, if we look at another equation, y equal to x cubed, and we look at a point 2, 8 and a point negative 2, negative 8, And if we draw a few more points on here, we see that the point 2, 8 and the point -2, -8 are reflections of each other through the origin. And so we could pick any general point x, y, and a point -x, -y, and the same would be true, and so we could say the ordered pair xy and -x, -y are symmetric with respect to the origin. And so we could say the graph of y equal to x cubed is symmetric with respect to the origin. So far, what we've done is look at graphs and visually inspect them to see if they look symmetric with respect to either the x-axis, the y-axis, or the origin. There are also algebraic tests of symmetry. And let me spell that correctly. And so let's look at what these are, and then I'll give you examples of how they're used. So if we're testing or looking to see if a graph is symmetric with respect to the x-axis, we can say if replacing y with -y produces an equivalent equation, then the graph is symmetric with respect to the x-axis. And then similarly, for the y-axis, if replacing x with -x produces an equivalent equation, then the graph is symmetric with respect to the y-axis. And for the origin, if replacing x with negative x and y with negative y produces an equivalent equation, then the graph is symmetric with respect to the origin. So let's see how this works. Let's look at the first equation we saw a graph of, y equal to, x equal to y squared, which was this horizontal parabola. And we saw that by visually inspecting that it looked symmetric with respect to the x-axis. And our algebraic test for that is to replace y with negative y. So let's replace y with negative y to test for symmetry with respect to the x-axis. And so we'll have x equals negative y in parentheses squared. And so if we simplify that, we get x equals y squared. And this is equivalent to the original equation. And so the graph is symmetric with respect to the x-axis. Okay, now let's test our second equation that we saw, which was y equal to x squared minus 5. And it seemed to be symmetric with respect to the y-axis. So let's replace, if you notice, it's the opposite variable if we're testing for symmetry with respect to the x-axis, as we did above here. We replace the opposite variable with its negative. Here we're testing for symmetry with respect to the x-axis, so we replace y. I don't think I said that right. We're testing for symmetry with respect to the y-axis, so we replace x with negative x. And so we'll have y equals negative x quantity squared minus 5. And if we simplify that, we get y equals x squared minus 5, which is equivalent to the original equation. And so the graph is symmetric with respect to the y-axis. Okay, so now let's look at the third equation we had, y equal to x cubed. And to algebraically show or test to see that it's symmetric with respect to the origin, we want to replace x with negative x and y both, and y with negative y. And so we'll have negative y equals negative x cubed, and that simplifies to negative y equals negative x cubed. And now, can we make this equivalent to the original? Well, yes, if we multiply both sides by negative 1, we get y equals x cubed, and then this is equivalent to the original equation, Therefore, the graph is symmetric with respect to the origin. Okay. Now let's take an equation that we haven't looked at yet. Let's look at 2x to the fourth plus 3 equals y squared. And the question or the directions will be determine whether the graph is symmetric with respect to the x-axis, y-axis, or the origin. So we want to apply those 3 tests to this one particular equation. Okay, so let's test for symmetry with respect to the x-axis. So that means replace y with negative y. Okay, so we'll have 2x to the fourth plus 3 equals negative y quantity squared. And that gives us an equivalent equation. So yes, we have symmetry with respect, I'm going to abbreviate WRT, with respect to the x-axis. And then let's test for the y-axis. So we'll replace x with negative x, and we get 2 negative x to the fourth plus 3 equals y squared, and that simplifies to 2x to the fourth plus 3 equals y squared. And so, yes, we have symmetry with respect to the y-axis. And then if we test for symmetry with respect to the origin, we'll replace x with negative x and y with negative y. And so we'll have 2 negative x to the fourth plus 3 equals negative y squared. And that simplifies to 2x to the fourth plus 3 equals y squared. So we have symmetry with respect to the origin. And let me share with you one more thing here. If we have any two of these symmetries, the third will automatically be symmetric also. Okay, so what I've done so I can show you that these are symmetric is I've taken this equation and I've written it with the y squared on the left. Y squared equals 2x to the fourth plus 3. And I've solved for y. And so I get plus square root of 2x to the fourth plus 3. And y equals negative square root of 2x to the fourth plus 3. And then I've graphed these. Let's see, hopefully you can see this. And we have the top half of the graph and the bottom half of the graph. And so you can see it's symmetric with respect to the y-axis, the x-axis, and the origin. So we were right in our test. Okay, so that's how we would test, by plugging in to show symmetry with respect to the x-axis, with respect to the y-axis, and with respect to the origin. Now, let's look at just some points and some of the problems that we'll see in our homework assignment is to find the point that is symmetric to the given point with respect to the x-axis, y-axis, and the origin. So if I have the point -5, 6, it's helpful if we put that point on a graph. 1, 2, 3, 4, 5, -5, 4, 5, 6. And so here's our point. And so if we're looking for a point that's symmetric to this point with respect to the x-axis, we find the point on the opposite side of the x-axis and then just determine what the coordinates of that point are. Well, it will have the same x, so -5, but opposite sign for y, so -6. And then if we want the point that's symmetric to our original point with respect to the y-axis, we'll find that point opposite, equidistant, opposite the y-axis. And then what are the coordinates of that point? Well, instead of -5, it would be 5, but it will have the same y value, so 5, 6. And then if we want the point that's symmetric to our original point, symmetric with the origin, we find a point, go through the origin, equidistant on the other side of the origin, and we would have the same numerical values but opposite signs, and so we would have the point 5 and -6. Now, symmetry can also be used in determining whether a function is odd, even, or neither. So we want to see what that means. And so let's do this. Even and odd functions, and odd. Okay, so if the graph of a function f is symmetric with respect to the y-axis, we say that it is an even function. That is, for each x in the domain of f, f of x equals f of -x. And if we stop and think about that for a minute, if it's symmetric with respect to the y-axis, that means it's, to determine that in our testing, we changed the sign of the x value, and so that would make this equation true. F of x equals f of -x. And then if the graph of a function f is symmetric with respect to the origin, we say that it is an odd function. That is, for each x in the domain of f, f of -x equals negative f of x. So here we can think, well, we're changing both the sign of x and the sign of y, because f of x is just another way of writing y. So we would just use the same tests for symmetry with respect to the y-axis to determine if the function is even, and for symmetry with respect to the origin to determine if the function is an odd function. There is no term that would describe something that was symmetric with respect to the x-axis, because those graphs would not be even functions. Okay, so an example of this would be determine whether the function is even, odd, or neither, or we could say neither odd nor even. And so if we have the function f of x equals negative 3x cubed plus 2x, we would substitute y, first of all, negative 3x cubed plus 2x, and then to determine if it were even, we test for symmetry with respect to the y-axis, asking, is it even? And so we'll substitute x for, or negative x for x, so we'll have y equals negative 3 and then negative x cubed plus 2 times negative x. And let's simplify this. So if we cube negative x, we get a negative x cubed times negative 3